Hello mathematicians, we're now going to have a look at the motion of a particle falling downwards in a resisting medium and under the influence of gravity. This is essentially the case of free fall, vertical motion. I'm going to use x double dot rather than y double dot. The variable is irrelevant. So if I take upwards as positive, then I'm going to have, for the falling object, the acceleration due to gravity causing a downward force of mg, and there'll be a resistive force due to the air resistance, and that will point upwards, and it will be of magnitude r. So my vertical, or my overall force, is minus mg plus r with these sign conventions, so be careful about sign conventions. Now notice that if we're falling under the influence of gravity in a resistive medium, you'll generally reach a terminal velocity, and the terminal velocity occurs as time tends towards infinity. Whatever the limiting value of v on t is, that's our terminal velocity. I guess you could also think of it as when x tends to infinity, if we've got v as a function of x, or alternatively, from a physics perspective, you have terminal velocity when you have net acceleration of being zero, which occurs when net force is zero. Now just a little sideline, the reason there's a frog here is because in the dark distant past, one of our physics experiments involved terminal velocity of frogs, and if we dropped a frog, we noticed that it's flung its arms and legs out to increase its surface area. Therefore the resistance against, or the air resistance increased, trying to hold it up a little bit. So it was like parachuting, and the frog could survive relatively unscathed from a medium drop. So let's have a look at some examples. So as always, it's getting the signs right and the setup correct to give you a chance of doing your maths correctly. So if we're falling through the air at a velocity v, which sort of means by implication that they're taking downwards as positive, we encounter a resistance of v on 6 newtons per unit mass. So the per unit mass implies that v on 6 is the acceleration or retardation. Using g equals 10, then do these things. Position an expression for velocity as basically as a function of time, for position in terms of v, which means v as a function of x, and terminal velocity, which we saw is the limit as t tends towards infinity. So let's get our setup correct. So here we've got the object falling down. If we're going to take down as the positive direction, then t is 0, x is 0, and although it doesn't expressly say it, we're going to assume that he was falling from rest at the first time we observed him. So sometime later he'll have this displacement, so it will be x rather than minus x because I've taken downwards as positive, and again v as v rather than minus v, because although velocity is pointing downwards, we're going to take downwards as positive. So what are the forces acting? So the forces acting are mg, which is 10 times m, and it's downwards, so it's going to be positive. And we'll have a resistive force which is acting upwards, and it's the mass, the number of mass units times v on 6. Now it's pointing upwards, so when we set up our vector equation, we'll have to give it a negative sign. So our acceleration is mg minus r. Divide through by the m, and we get this equation for acceleration. Now given that we want to find velocity as a function of t, we'll use dv dt as our expression for acceleration. And we know that we want to be able to rearrange this, so we have to, given if we're going to break up our integral into dv's and dt's, we need just one expression here, so I have to rewrite this as a single fraction. I can't add and subtract things, I need to be able to multiply and divide. So that's so that I can take the 60 minus v, divide that over the other side when I'm just doing dv from 0 to v. That should have another, oh no, that's okay. And over here, I have my 1/6, or the 6 on the bottom still there, and I'm integrating t from 0 to t. So that clearly becomes t on 6. Now when I integrate this side here, I would like it to have -1 up the top, so if I take negative out the front here, that integral becomes log of 60 minus v from v to 0. If I then take that minus over to the other side and substitute in my limits, use my log laws, and then take the exponential of both sides, I get to this part, and if I make v the subject, I get to this, my equation for velocity as a function of time. Now part 2 was about getting my velocity as a function of displacement. So if I take my initial equation, this one here, I now want my acceleration in the form v dv dx to carry out my integration. So I bring my 60 minus v over, so this integral is the same, and on the other side I've got 1/6 the integral of dx, which of course comes out to be that. So in a sense we've set the problem up. Now we actually have to deal with this integral. So we've had pretty straightforward integrals up to now, but this is one which is not quite so straightforward. Partial fractions don't work, top is not the differential of the bottom. So partial fractions don't work because we can't factorize the bottom. So in that case, you might remember that what we can do is carry out long division. So if I take this and do my process of long division, it means that I can write v on 60 minus v as this. Now both those parts are easily integrable. So my integral becomes the integral of -1 plus the integral of 60 on 60 minus v. So the first part is okay, it just becomes -v. And then my second part, again, I would like to take the 60 through the integral sign. I'd like -1 up the top. So I've got -60 outside the log of 60 minus v from v to 0. So substituting in my limits, I get this, which using my log laws gives me this, and then using my power rule for the log laws gives me this. So going right back to our initial integral, that means that x on 6 equals this expression that I've just got. Multiply both sides by 6, and this becomes my expression for displacement as a function of velocity. Now for terminal velocity, we simply remember that terminal velocity is the expression for v as a function of t as t tends to infinity. So from part 1, where we had our expression for v, then if I put t heading to infinity, the exponential term heads towards 0, so the terminal velocity is 60 meters per second. Now for the last part, if we were using a parachute and therefore the air resistance increased by a factor of 12, to work out the terminal velocity we can take our original expression, which was 10 minus v on 6, and we're just going to increase that air resistance by a factor of 12. So that then simplifies to 10 minus 2v. So once we have that, then it's a relatively easy integral to do. So divide the 10 minus 2v across, and on the other side it's just the integral of t. So that gives us this integral, straight log, and a t on the right hand side. Multiply through by -2 and plug in the limits. Take the exponential of both sides This gives us our expression for velocity as a function of time, and as above, as time tends towards infinity, that means the exponential term will disappear, so v will equal 5. That's probably not the only way to do that. We could have perhaps also made use of the fact that at equilibrium, so at terminal velocity, the downward force equals the upward force, and we could have solved those two force equations. I'll leave that for you to think about. But have a go at these examples out of set 2. Obviously the bulk of set 2 is about these sorts of questions.